Hi everyone, let's talk about today's LeetCode daily challenge. This is a classic problem, and by classic I mean this is very similar to the coin change problem. Let's read the problem. Given an integer n, return the least number of perfect square numbers that sum to n. Okay, what is a perfect square? A perfect square is, an integer that is a square of an integer, like 1 times 1, 2 times 2, 3 times 3, 4 times 4. We have seen these numbers. And now we want to change number n using these perfect squares. Very similar to coin change problem. If we look at the first example, we can change 12 with 3 4s. Or in the second example, we can change 13 with 4 and 9. So how do we think about this problem? So the first thing is take a look at the constraint. And it is 10 to the 4. N could be as big as 10 to the 4. The next thing that you can think about is how many perfect squares do we have in this range from 1 to 10 to the 4? How many perfect squares do we have? So in order to find that number, you should take a square root of this number, which is 10 to the 2. So we only have 100 perfect squares in this range. So, okay, so what do I do now? That's a good question. So when you have a problem like this, and you probably don't have the idea how to tackle it and how to solve it, you just take a number like 12 and go and try to solve it for that number 12. For example, here, when you want to change 12, you have several options. You can, for the first coin, I'm going to call them coins, or perfect square. For the first perfect square, you have several options. You can either take 1. In that case, you will be having 11, and then you should solve 11 if you take 1. If you take 4, which is the next perfect square, you will have 8, and then you should solve 8 in order to find the answer to this path, which was taking 4. The next one is taking 9, next perfect square, and then you will have 3, and so on. That's actually the last thing you can take from 12. The next one is 16, which you cannot use in this case because it's bigger than 12, of course. So in this case, your answer, without going any further, your answer is going to be minimum of f of 11 plus 1. F of 11 plus 1, because if you can solve 11 and find the minimum number of coins, minimum number of perfect squares to change 11, then you will add just 1 and then you will build 12. Or f of 8 plus 1. Again, if you can solve the problem for 8, then solving 12 would be just adding a 4 to that set of perfect squares that builds 8. Or it's going to be f of 3 plus 1. So this is how you can think about it. Like, take a number and try to solve it, and then say, okay, what options do I have? Okay, I can take 1 probably. I can take 4. I can take 9. Oh, so many options. So many options. So whenever you see a problem that you have so many options, that is a hint that you can apply dynamic programming. If you have many options and you don't know which one to apply, it's time to try dynamic programming. Maybe this is not the solution, but this is something worth considering. So how do we know if this is the answer? If we can actually apply dynamic programming? If you have optimal substructure, and if you have overlapping subproblems. What does that mean? So let's try f of 100. F of 100. Okay, when you're trying f of 100, you will have several options. So it's either going to be taking 1 and it's going to be f of 99. Or you're going to take 4 and it's going to be f of 96. Or it's going to be or you're going to take 9 and it's going to be f of 91. And so on. Okay? And somewhere here, when you are solving f of 99, you may need to calculate, so like somewhere here, down here, you may need to calculate f of 91. So this is overlapping subproblem. You have f of 91 here and f of 91 here. So in order to solve this 100, you just need to solve f of 91 once. And after that, you can save the answer, and any of the subsequent calls, any time later, if you want the answer to f of 91, you know you have saved the answer. This is overlapping subproblem. So the ingredients of this dynamic programming approach are first this one, which is the recursion formula. And what does that mean? Let's talk about this. Recursion formula. That means that in order to find the answer to n, in this case 12, if the function f gives you the answer of 11, the answer of 8, and the answer of 3, then you have the answer of 12. And that is this, minimum of f11 plus 1, f8 plus 1, and f3 plus 1. This is the recursion formula. This is how you are building up the answer of 12 based on smaller subproblems. So we have the recursion formula. We have the overlapping subproblem. We just need to think about the base case, and then we are done. We have a dynamic programming approach. What is the base case? In this case, what is the base case? I'm going to pause 2 seconds. The base case is something that you can simply answer without running a program, without writing anything. You can calculate it with pen and paper. In some cases, you can actually just tell me. And in this case, it's going to be f of 0. F of 0 is going to be 0. And that means in order to change 0, how many coins do you need? Nothing, 0. So this is the base case, and we are done. We are done. We have a solution for ourselves. Recursion formula, overlapping subproblems, and of course the base case. Let's go and write the code and see how we can implement this. So we need to define a function f, right? First, we can take care of the base case. Then we can do this recursion formula, like call any of the smaller subproblems and take the minimum among all of them. So the result is going to be, at first, it's going to be n, because n is the worst case for n. You can have 1, 1, 1, 1, 1, n times. So you can add n here. And then while d times d is less than or equal to n, so this is how you can build perfect squares. Like d times d is the perfect square, and you are saying, hey, while my perfect square is less than or equal to n, continue this iteration, this for loop. And result is going to be minimum of result and f of n minus d times d plus 1. So this is exactly what we were doing there. F of n minus d times d plus 1. F of n minus d times d plus 1. And we take the minimum among all of them. and then here we return result. Okay, and here we just return f of n. But there's some problem with this. We have not memoized the subproblems. Let me show you. So if I just see out like if n is equal to 8, I'm gonna see out this is 8, and let's see how many times, like for 12, let's see how many times we are printing this is 8. We are printing 2 times, and that is problematic. So if I change this to 17, if n is 17, it's going to be even more. You see? So we are calculating the answer for f this number of times, like 10, 11 times. That's a lot, and we shouldn't be doing that. We should just save the answer, and any of the subsequent calls should just look up the answer and return that. And in order to do that, we need a table. We need a table. I'm going to call that dp. And before we start our like recursive calls, we should initialize dp. So I'm going to resize it to n plus 1, and I'm going to initialize it with -1. So -1 means that this subproblem is not calculated yet. So if I go here and I say if dp of n is not equal to -1, return dp of n. That means if this subproblem has already been calculated, just return it. Okay, and then I will do the calculation, and at the end I'm going to save it before returning. This is, you can do it, this is allowed in C++. You can say dpn equals result and then return the value. And if I run this problem, this code again, you will see that this is 8 is going to be printed only once. Only once. So this is how we memoize and stop calculating subproblems again and again. So I'm going to delete this and try a bigger test case, probably something like 2000. Good. And I'm gonna submit. Okay, so this is the top-down approach. Can you think how about the bottom-up approach and see how we can implement this in a bottom-up way? And if you have any questions, ask me in the comments. Thank you.